In this session on basic ideas regarding regression, we are focusing on a sample regression function. Most often, we have to estimate the population regression function on the basis of sample information. It is very difficult to collect information from the entire items of the population, and often we collect information from a representative sample, and on the basis of that sample information we have to estimate the population regression function. If we have only information on randomly selected sample of y values for fixed x values, the critical question is, can we estimate the population regression function from the sample data? So it is a very difficult task. We have to estimate the population regression function on the basis of sample data. When we have two samples, we can draw two regression lines based on information provided by the two samples. In general, we can say that if there are n samples, we can draw n different regression lines based on those n samples. And analogous to the population regression function, we have the sample regression function, SRF. While PRF denotes population regression function, SRF shows sample regression function. So this is the equation which represents sample regression function. Y hat is equal to beta 1 hat plus beta 2 hat xi. Here, this should be read as yi hat or yi cap. Yi hat is equal to beta 1 hat plus beta 2 hat xi, where yi hat is an estimator of the expected value of y for a given value of xi. We have examined expected value of y for a given value of xi in the case of population regression function. This is a conditional expectation. And here yi hat is an estimator of the expected value of y for a given value of xi, and beta 1 hat is an estimator of beta 1, and beta 2 hat is an estimator of the population parameter beta 2. Here you have to remember that beta 1 and beta 2 are the true values of the population parameters, and we are always concerned with the estimation of the population parameters, and beta 1 hat and beta 2 hat are estimators of the true population parameters beta 1 and beta 2. So this is a sample regression function. So sample regression function is slightly different from population regression function. Sample regression function is written like this: yi hat is equal to beta 1 hat plus beta 2 hat xi, where yi is the estimator of expected value of y given xi, and beta 1 hat is the estimator of true population parameter beta 1, and beta 2 hat is an estimator of the true population parameter beta 2. So what is an estimator? Estimator is also known as sample statistic. So estimator is a rule or a formula or a method that tells how to estimate the population parameter from the information provided by the sample. As I have already mentioned, we are always trying to estimate the population parameter from the information provided by the sample, and estimators help us to estimate the true population parameter from the sample data on the basis of sample data. So estimators are rules or formulae or methods which are used to estimate the population parameter from the information provided by the sample. So when we use an estimator, we get a unique numerical value for that estimator. The particular numerical value obtained by the estimator in a specific application is known as an estimate. See, for example, when you estimate the marginal propensity to consume, in the case of a consumption function, if you get a value like this, beta 2 hat is equal to 0.72, that value is an estimate. Beta 2 hat is an estimator, and 0.72, that is the estimate. So estimate is the particular numerical value obtained by the estimator in a specific application. So you must be able to distinguish between estimator and estimate. Estimator is a method or rule or formula that help us to estimate the population parameter from the information provided by the sample. However, estimate is the numerical value obtained by the estimator in a particular application. Now let us make the sample regression function in the stochastic form. We are introducing the stochastic variable also into the sample regression form. So here you have to remember that whenever you introduce the stochastic term, in the left hand side you have to write ya, actual observation of y. So actual observation of y is equal to beta 1 hat plus beta 2 hat xi plus ui hat. This is the sample regression function in stochastic form. So yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat, where ui denotes the sample residual term. In the case of population regression function also, we have made it, we have converted it into stochastic form by introducing the random term u. Here ui hat denotes the sample residual term, and conceptually ui hat is analogous to ui, and this is the sample regression function in stochastic term. In stochastic form, yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. So in any regression analysis, our aim is to estimate the population regression function yi is equal to beta 1 plus beta 2 xi plus ui on the basis of information provided by the sample. That is, on the basis of sample regression function, yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. So as I have already mentioned, our ultimate aim is to estimate the population regression function. We want to find out the values of true population parameters beta 1 and beta 2. So we have to estimate the population regression function, which is in the form yi is equal to beta 1 plus beta 2 xi plus ui on the basis of sample regression function. So sample regression function is this: yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat, where beta 1 hat is an estimator of the true population parameter beta 1 and beta 2 hat is an estimator of the true population parameter beta 2. So here in the graph you can find a sample regression function and a population regression function. So we have sample and population regression lines. So population regression function is denoted by PRF and sample regression function is denoted by SRF. The dotted line is the sample regression function and the other line represents the population regression function. So here income is taken along the x-axis and consumption expenditure is taken along the y-axis. And you can see that the actual observation of y, which is denoted by yi, it is different from both yi hat and expected value of y given xi. So expected value of y given xi, conditional expectation of y, that is in the population regression function, and as we have already seen, yi hat is the estimated value of y on the basis of information provided by the sample, and it lies on the sample regression function. So difference between yi and expected value of y given xi, that is deviation of actual observation of y from the conditional expectation of y, is denoted by ui. So that is ui is equal to yi minus expected value of y given xi, and the estimated value of y on the basis of sample regression function, that is denoted by yi hat. So difference between yi, actual observation of y, from the estimated value of y, yi hat is denoted by ui hat. So on the basis of sample regression function, observed value of yi, observed value of the dependent variable yi is equal to yi hat plus ui hat, where yi hat is the estimated value of y on the basis of sample regression function, and ui hat is an estimator of the residual term. On the basis of population regression function, observed value of yi is equal to expected value of y given xi plus ui. So because of sampling fluctuations, estimate of the population based on sample regression function is at best an approximation of the true population regression function. So we know that whenever we try to estimate a population regression function on the basis of sample regression function, there may be sampling fluctuations, and as a result of those sampling fluctuations, the estimate of the population based on sample regression function will be at best an approximation of the true population regression function. Now, why actual observations of the dependent variable deviate from the regression line? That is, why actual observations of the dependent variable deviate from the estimated values of the dependent variable. Actually, this shows the significance of the stochastic term in our econometric model. So what are the reasons for deviation of observations from the estimated values? So here there are some important reasons which lead to the deviation of observations from the regression line. The most important reason is omission of variables from the function. We know that it is very difficult to include all factors which influence the dependent variable in a regression function. We will include only the important variables. See, for example, in the demand function, we know that the price of a particular quantity is the most price of a particular commodity is the most important factor which influence quantity demanded of that commodity. However, from the real world experience, we know that there are a large number of factors other than price which can influence demand for a commodity. So in a simple linear regression model, we will include only one explanatory variable, and in a multiple regression model, we will include more than one explanatory variables. So we can include factors like apart from price of the commodity, we can include income of the consumer, price of related commodities, taste and preferences of consumers, etc. in the model. However, we know that there are a large number of other factors which can influence demand for a particular commodity. So we have to omit many variables which can influence the dependent variable from a regression equation. So omitted explanatory variables is an important reason for the deviation of observations, and in any regression model, the stochastic term represents all the explanatory variables that are omitted from the function. So that is one of the major reasons for deviation of observations from the regression line. Then we know that human behavior is unpredictable. So random behavior of human beings, that is another reason for the deviation of observations. And another reason is the imperfect specification of the mathematical form of the model. Mathematical form of the model, sometimes we may be specifying the incorrect form of the mathematical model. So imperfect specification of the mathematical form is another reason for deviation. Then there are errors of aggregation, then there are errors of measurement. All these type of errors also lead to deviation of actual observations from the regression line. So the critical question is, given the fact that sample regression function is an approximation of the population regression function, can we devise a rule or a method that will make sample regression function as close as possible to the population regression function? Always our aim is to make the sample regression function as close as possible to the population regression function. So can we devise a rule or a method that will make sample regression function as close as possible to the population regression function? So how should the sample regression function be constructed so that beta 1 hat and beta 2 hat is as close as possible to the true beta 2, even though true beta 1 and beta 2 are not known? See, we do not know the true value of population parameters beta 1 and beta 2. So our aim is to construct the sample regression function in such a way that beta 1 hat is as close as possible to beta 1 and beta 2 hat is as close as possible to beta 2. So can we devise a rule or a method that will make beta 1 hat as close as possible to true beta 1 and beta 2 hat as close as possible to true beta 2? So in a simple linear regression model, we will try to find out some techniques which enable us to make beta 1 hat as close as possible to beta 1 and beta 2 hat as close as possible to beta 2.